SciPAD, page 160. Torque, so a year 12 concept, something you should be relatively familiar with, although a number of you may have struggled with that last year. So torque, with a symbol TOR, is a measure of how much force is acting on an object that causes the object to rotate. Okay, so it's all about causing rotation. Torque is created when a force is applied at some perpendicular distance, and so we normally have a little right angle symbol down here to say that the force is at right angles to the distance. Last year it would have been force times distance, so we'd have had typically this formula here, and this year we're saying force times radius. Both are essentially a distance, except for a rotating object we call it distance. In the same way that a force causes an object to accelerate, a torque causes an object to experience angular acceleration. Okay, and so that's what we care about in year 12, and so in year 13, and so that's what we're going to begin to look at. And so in translational motion, you had Newton's second law, F equals ma, and now we're going to, what's a rotational equivalent of force? Well, it's a torque. What's a rotational equivalent of mass? Well, yeah, interesting. It's something called rotational inertia. So mass is really inertia, and now we're going to be looking at something called rotational inertia. An object's rotational inertia is a measure of that object's resistance to change. Not it's just resistance to motion, but it's resistance to the rotational motion. And so we get tau equals I alpha, which is a really important equation, and we're going to spend a bit of time drawing graphs of torque versus angular acceleration, where the gradient is going to give us I, but not wanting to jump too far ahead of ourselves. If more than one torque is present, then the net torque must be determined before calculating angular acceleration. So we have something that is 0.78 meters long, and it's got a mass of 1.25 kilograms. And it says calculate the weight on the rod. Well, we know mass times gravity. We've now made it to year 13, and so it's going to be 1.25 times 9.81, where gravity goes up by one significant figure from last year, and we should get 12.2625 newtons, and because it's three significant figures, that should be to three significant figures, 12.3 newtons. Outline why the weight of the rod acts in the middle. The reason it acts in the middle is because that's where the center of mass is, because we're assuming that it is a uniform rod. C, calculate the torque acting on the rod. Well, we know that torque equals force times distance, or force times radius, and we know that if that's the pivot point, then that's going to be halfway, and so we go 0.78 divided by 2, and they've already kind of indicated that up here as 0.39, and so we're going to go 12.2625 times 0.39, and that's going to give us an answer of 4.78 Newton meters. Force measured in newtons, distance measured in meters, we get a unit of Newton meters. It says the rotational inertia of the rod, so I is 18.9 kgs per meter squared. At the moment the rod is released. To find out the angular acceleration and the translational acceleration at the far end of the rod. So the angular acceleration, we're going to use tau equals I alpha. We're looking for alpha, and so it's tau divided by I. The torque is 4.78 Newton meters. The rotational inertia is 18.9. If I divide those two numbers together, I get 0.253 radians per second. Now, if I want to work out the translational acceleration, I'm going to be using A equals R alpha. So translational acceleration equals the radius, which in our case is 0.39. Oh, it's not actually, is it? Because we're not asking what the acceleration is at the center, we're asking what the angular acceleration, linear acceleration is at the end here. So it's going to be 0.78. Well, that's a trick. 0.78 times the acceleration of 0.253. You may say, can we use this 253? Yes, because actually the angular acceleration is the same regardless of whereabouts on the radius you're measuring it. And so we do get a linear acceleration of 0.197 meters per second. That is that page done.